So hi everyone. So today we have a great pleasure of welcoming Richard Samworth, who is the director of the Statistical Laboratory at the University of Cambridge and who was the co-editor of the Annals of Statistics until last December. And today he will talk about optimal subgroup selection. So thank you for giving a talk.
Thank you very much, Anthony, for the kind invitation. I was just looking at the names coming in and I realized that I don't know so many people who are listening today, and that unfortunately means I don't know too much about the backgrounds of the people I'm speaking to, which makes me feel like I might be running the risk that I'm assuming things or something that people aren't so familiar with. So feel free to interrupt me if that's the case. Actually, this is a topic that's very new for me, so it might be a case of the blind leading the blind. Let's see. So the work I'm going to speak about today is joint work with two fantastic collaborators. Henry Reeve is a new lecturer at the University of Bristol, and Tim Cannings was my PhD student and postdoc. Then he spent some time at the University of Southern California, and now he's back in the UK as a lecturer at Edinburgh. Okay, so to set the scene for the problem I want to talk about today, I want to imagine, this might take quite a leap of imagination, but just see if you can. Imagine that you're really desperate to create a vaccine for a deadly virus, a drug or a vaccine, let's say. And you've been running this long clinical trial, you've done huge amounts of research to develop your product, and today is D-Day, where you get to find out whether the drug or the vaccine works. And you open the envelope, and oh no, it's a disaster. The trial failed. So we needed 80% efficacy in order to get approved by the regulators, but it's only 70%. So this is a very unfortunate, but unfortunately a very common occurrence in randomized clinical trials. And of course, it's very disappointing for everyone concerned. But just before you discard all the research that's gone into this development, one of your colleagues comes up with the following. They say, well, hang on a minute. If we just look at women over 50, then the efficacy is 95%. That sounds very impressive. Can we just give it to them? So that would be a very nice way of rescuing a sort of failed clinical trial if that were allowed. But I think instinctively our reaction to that is something like that, right? We're pretty worried about the prospect of just doing this. And so we need to think to ourselves, well, why are we worried about this? 95% does sound like a very high number. And so the key issue here, and what sort of drives this problem, is that the subgroup, in this case was the women over 50, was chosen after seeing the data. Okay, so all sorts of phrases like cherry picking and data dredging and data snooping and p-hacking, and probably some rather even worse phrases are thrown at people who do this, and it's generally known to be a bad thing. In fact, there's a large literature on why you shouldn't do subgroup selection. There are many tens of papers about it. I picked out a couple of quotes. Here's one, and analyses must be predefined, carefully justified, and limited to a few clinically important questions, and post hoc observations, that is made after seeing the data, should be treated with skepticism irrespective of their statistical significance. That's one interesting quote. And here's another one. The statisticians are right in denouncing subgroups that are formed post hoc from exercises in pure data dredging. Okay, so having said that this is definitely something that everyone knows we shouldn't be doing, it is, of course, exactly what we're going to try and do in this talk. And we're going to try and formally justify how you can select subgroups after seeing the data in an appropriate way with theoretical guarantees. To set this work in a little bit of context, subgroup selection is part of a larger field of subgroup analysis, and the aim of that field is to study the association between a response and subgroups of subjects as defined by one or more subgrouping variables. Okay, let me just get a little bit more formal about what we're planning to do then. I'm going to be given independent covariate response pairs and a family curly A of subsets of our feature space. And what we're going to aim to do is to define a data-dependent selection set, and I'll call that A hat, and it's going to take values in our family curly A, and I want it to have two properties. The first very important property, and a very stringent property, stringent requirement in many ways, is that I want it to have the type 1 error control in the following sense. I want that with probability at least 1 minus alpha, the regression function should be uniformly no smaller than the level tour on A hat. So the alpha here and the level tour, I'm assuming, are predefined. So the tour would be the efficacy level at which the regulator is going to approve your drug or your vaccine. So it was 0.8 or 80% in the example I presented at the beginning. And alpha would typically be some small level like 5% or something like that. But of course, it's very easy to satisfy that requirement just by outputting the empty set, and that's not very interesting to us. So subject to that requirement, I want the proportion of the population belonging to this data-dependent selection set A hat to be as large as possible. And another sort of desideratum here is that I want the family A to be of relatively low complexity to ensure an interpretable decision rule. So in the case of the women over 50, that would represent a hyperrectangle in my space. And in fact, if you think throughout this talk of curly A being a family of hyperrectangles, then I think that would be pretty fine, to be honest. Okay, now I will try and set things up in mathematical notation then. So my covariate response pairs are going to be denoted XY. The covariates taking values in space R to the D, and my response is going to be take values in the unit interval 0, 1. So it could be just a binary response, a label either 0 or 1, but it can be a continuous response too. But in that case, I want to think of it as being bounded. I'll write mu for the distribution of x, marginal distribution of x, and eta for the regression function. So between them, the mu and the eta define the joint distribution P. The family that's given to me is going to be a subset of the set of all Borel sets on R to the D, and I'll go assume just for technical reasons that the empty set belongs to this family. And some notation that's going to be very convenient is to talk about the Tor super level set of eta. So that's the set of points x for which eta of x is greater than or equal to Tor. And I'll write that as curly x Tor of eta. So the point here is that if you told me the underlying distribution P, then the best set I could output would be one whose measure was the supremum of the measures of all sets A, where A both belongs to my family and is a subset of the power set of the and belongs to the power set of this Tor super level set of eta. So it's a subset of this Tor super level set. So that's certainly the best I could do if you told me the P, but of course you don't tell me the P, and instead I just get to see data. So I have a sample of size n consisting of independent copies of x, y. And then I need to say what I mean by a data-dependent selection set. So that's a function. It takes as input my data, that is the xi, yi pairs, and it returns an element of my family curly A, and there's a very mild measurability requirement that I want this function to have. Okay, so I'm going to look for a data-dependent selection set, an A hat. So it's going to take data as an input, and it's going to return an element of my family A. How can I encapsulate this type 1 error control requirement? So to formalize it, I'm going to restrict myself to a family curly P of distributions on R to the D equals 0, 1 for my pairs X, Y. I'll place some restrictions on that family later on, but for now, let's just think of this as a generic family of distributions. And the data-dependent selection sets that satisfy my type 1 error control requirements are the ones for which uniformly over the class of distributions curly P, the probability that my data-dependent selection set is a subset of the Tor superlevel set of eta should be at least 1 minus alpha. So that is the set of such data-dependent selection sets is a subset of all of them, and I'll write this subset as a curly A hat n with a Tor, an alpha, and a curly P. So I want to output something belonging to this set, and then I know it satisfies my type 1 error control requirement. And subject to belonging to that set, remember we said we wanted the set we output to be as big as possible, and I'm going to measure that in terms of what I'll call a regret. And the regret here is the difference between the measure of the optimal measure we get output. That's this M Tor that I defined before. In general, I'm not going to be able to attain that always, but I can think about looking at the difference between the level M Tor and the conditional expectation of mu of A hat, conditional on A hat belonging to this Tor superlevel set of eta. So I don't care how big the set is when it isn't a subset of this Tor superlevel set, but I only care about how big it is when it is a subset, and I want it to be as big as possible. Okay, so our first result is actually a rather negative result, and it's going to tell me that just knowing, for instance, that the regression function eta is a Lipschitz function is not going to be enough to be able to output non-trivial data-dependent selection sets with type 1 error control. So curly P lip is going to be that whole family, and I'm actually going to introduce what I call a data-independent selection set. This is one for which, whether or not I output the set A and my data are independent for every set A. I'll write curly A bar for the sort of data-independent selection sets. So the rather negative conclusion of these hypotheses is that if my A hat controls the type 1 error probability over this class of Lipschitz regression function distributions, then with high probability, with probably at least 1 minus alpha, it has to output a set of measure 0 whenever it is a subset of, or conditional on it being a subset of the Tor superlevel set of eta. So that's rather disappointing. And a consequence of that is that its regret is bounded below by 1 minus alpha times M Tor. And unfortunately, I can get arbitrarily close to that level using a data-independent selection set. So that's really telling me that this is hopeless, and that I need further constraints on my problem in order to be able to make any progress. And really, the issue here is that even though I know my regression function here is Lipschitz, I don't have any control over the Lipschitz constant. And so the way we're going to try and make progress is to restrict our attention to known holder classes, that is, both where we know the holder exponent and the holder constant. Now, initially, I'm just going to think about holder exponents beta being less than or equal to 1. I will generalize that later on, but it helps in terms of the notation a little bit but there are actually more fundamental reasons why this is a convenient restriction for the time being. But as I say, I will be able to relax it later on. Okay, so just a reminder then about the definition of what it means for a function to be holder, and it's convenient to work with the infinity norm on the right-hand side in this case, but it doesn't really make very much difference. You'd just get a different value of CS if you worked with a different norm, because we're on finite dimensional space. Another convenient notion is that of a lower density. I'll write this as omega. This is I'm going to constrain this lower density, and that's going to amount to a constraint on the marginal distribution of the feature vectors. This b bar r of x, that's the infinity norm ball of radius r about x. So its volume would actually be 2r all to the power d. So if I put a 2 to the d on the bottom, and I don't really care about just dimension-dependent constants in this work, so that's why I'm not putting the 2 on the bottom. So I'm dividing the measure of this ball essentially by the volume of the ball. And then I'm taking an infimum over r between 0 and 1. So if this were actually a limit as r goes to 0 rather than an infimum, and if mu were absolutely continuous with respect to the Lebesgue measure, then almost everywhere this would be essentially the density of the marginal distribution at the point x. But by working with the infimum, I can actually avoid any assumptions of needing to have an absolutely continuous distribution with respect to Lebesgue measure, or it being bounded away from 0 or anything like that. So this actually turns out to be a really convenient notion in all sorts of problems of this type. It's something that I worked with in a transfer learning paper very recently. So it's turned out to be very useful at least twice to me already. Okay, so having introduced those different definitions, the key definition for us is going to be the restrictions that we're going to make on the distributions that we consider. And this looks a bit forbidding, so I'll try and talk through it a little slowly. What this definition is talking about is how well we can approximate the sort of optimum or oracle selection set with some further restrictions. So on this left-hand side, notice that we've got A belonging to curly A, as we had before, and it also has to belong to the power set of this intersection here. So imagine that I didn't have this bit here, this lower density restriction, and that delta was 0. Well, in that case, I'm back to where I started, and the best I can do is to output a set of measure m tor. So notice that this m tor appears on the right-hand side. So in introducing this curly x psi of omega, which is saying that I need the lower density to be bounded below by psi on this set A, and introducing this delta, I'm imposing further restrictions on the set of A that I'm willing to consider, and that means that the supremum of the measure that I can attain is going to be smaller. And so what this definition is doing is controlling how quickly this sort of optimum I can get over these classes decays as I start to increase the level of the super level set from tor to tor plus delta, and as I start to introduce a lower bound on the lower density. So there are two different exponents that control this class. There's a kappa and the gamma, and the kappa is controlling the effect of the lower density, and the gamma is controlling the effect of the delta. So the gamma you can think of as being rather like a margin exponent, if you're familiar with the kind of Sibikov-Mammon margin exponent. Okay, let's have some examples to give some idea of what these classes mean. So the simplest situation I can imagine here is where I've just got a binary label with 50-50 probability of being 0 or 1, and Gaussian class conditional distributions with a different mean and a common variance. So one of the means is at nu, and the other means at minus nu. And then I'm just going to work with the class of intervals on R, closed intervals on R. So this is a picture that we've got here. The dotted lines are the individual class conditional components, the Gaussian components, and the black mixture density is the marginal distribution of the feature vectors. And then what I've plotted in red is related to the regression function. So the red curve is in fact the regression function, and the dot dashed line is this 80% level that I seem to have fixed for the threshold of belonging to this for how large I want the regression function to be. So in this case, it turns out that I can take both of the exponents to be 1, the kappa and the gamma to be 1. So the gamma, which remember is controlling the margin contribution, the fact that that's 1 is related to the fact that the regression function is crossing this level tau at an angle. So this is like a pretty regular situation in that sense. And that the fact that the kappa is 1 is related to the fact that the lower density is bounded below and bounded away from 0 on this set. So a slightly more complicated example in 2 dimensions, as I've got the picture here, but in d dimensions, one can think of this as well, would be a situation where your regression function is coordinate-wise increasing, and then I'm going to control the way in which the regression function grows as we move away from the tau level set, not the super level set, the tau level set of eta. And so if it grows fast enough that it's of order the distance from that set to the power 1 over gamma, then it turns out that I can take the exponent to be gamma in this class. And then the fact that I've got the uniform measure for the marginal means that actually, and that's bounded away from 0, of course, on its support, that means I can take the kappa to be arbitrarily large, at least provided I choose the constant to be sufficiently big. I've got one more example, which perhaps I won't go through in detail, but this is just an example where if you give me a kappa and you give me a gamma, I can come up with a distribution that belongs to this family for that choice of kappa and that choice of gamma. Okay, so the first main result I want to talk about today is providing minimax rates of convergence for the regret of my algorithm if it's controlling type 1 error over our classes. So the theorem comes in 2 parts. I fix a vector theta and a Holder exponent belonging to 0, 1. So the first part is giving us an upper bound on the regret, and so the supremum here is taken over all distributions for which the regression function eta is beta Holder with this Holder constant CS. And moreover, the distribution belongs to this approximable class for this choice of this kappa and gamma. Actually, the infimum, I can even control the type 1 error over a larger class of distributions, just those that for which the regression function is beta Holder with Holder constant CS. I don't need the approximable class restriction there. But what's interesting here is that it's really the first term in the minimum that's the interesting term, and particularly the first term is interesting here because the sort of constants allowed to depend on theta and the VC dimension of my class. I'm assuming I'm working with a finite VC dimension class, but I'm getting these parameters. The constant's not allowed to depend on either the n, obviously, but it's also not allowed to depend on the alpha. So I want to be able to claim that I'm getting the right dependence, and I'll try and justify that in a moment, on both the n and the alpha. And then we've got this rather interesting exponent for how fast this rate of convergence that we get, depending on this margin exponent, the exponent associated with the lower density and the Holder exponent and then the dimension. But I can't get a faster rate than the parametric rate of convergence, and that's this kind of 1/n⁻² term that's giving me this parametric rate floor. But in principle, one can have this going to 0 as n goes to infinity, and that's telling me that it is possible to output data-dependent selection sets that do well in terms of controlling the regret over families that satisfy the type 1 error control guarantee that we want. So complementing this upper bound is a corresponding lower bound. The lower bound has what I claim is a rather mild restriction on the parameters. This is, for those of you who are familiar with this is actually a little bit weaker than, but somewhat similar to a condition in Audiper and Tsibikov from 2007, which rules out sort of super fast rates. I think that it can be thought of as a rather mild condition. But the lower bound is of exactly the same order here. So this is the sort of exact minimax rate for this problem, which is rather satisfying. So let me talk a little bit about the algorithm that we use to achieve the upper bound. I'll need to talk about the empirical marginal distribution and the empirical regression function. The empirical margin distribution on a subset B of R to the D is just the number of data points, the number of feature vectors that lie in B. And the empirical regression function, eta hat n of B, is just like a Nadaraya-Watson estimator of the regression function. It's just a local constant estimator. And the key idea that underpins our algorithm is to define for every subset of R to the D, well, at least in principle for that, I'll restrict it later on, a p-value, what I claim is going to be a p-value. And this is a p-value for testing the null hypothesis that the infimum of the regression function over B is less than Tor. Okay, so that's going to be my null hypothesis. And I want to know if there's enough evidence to be able to reject that null hypothesis. So let's see what's going into this p-value construction here. And the key bit is what I've written as a KL here. That's the Kullback-Leibler divergence between Bernoulli distributions with these two different parameter values. Okay, so the idea is that if I'm under the null hypothesis, so the infimum of my true regression function is smaller than Tor on the set B, then the biggest it can be anywhere on B is this level, and that's by the Holder condition on the regression function. So the only way I have any evidence against the null hypothesis is if this empirical regression function is above that level. So notice that this p-value is only defined in this way when eta hat n of B exceeds this level, and otherwise we just define it to 1. In other words, we've got no evidence against the null hypothesis. But if this Kullback-Leibler divergence is big, that is giving me evidence against the null hypothesis, and I need to modulate that by the number of data points that I've got in that set. So the more data points I have in the set, the more sort of powerful that this evidence becomes. Okay, and this little lemma here is just confirming that with this definition of p hat n of B, this does indeed define a p-value. In fact, it's a p-value even conditional on the x data points. So of course I could uncondition this statement and just argue that this is a p-value. So in other words, whenever you give me a set B where the infimum is less than or equal to Tor, then the p hat n is a p-value in the sense that it's a super uniform random variable. Okay, so if I'm going to define an algorithm, then I can't define these p-values for every subset B of R to the D. And so in the end, I'm just going to do it for a finite set of hyperrectangles. These are hyperrectangles with sort of dyadic endpoints in each coordinate. that intersect the x values, the data points, they're kind of in the region that I care about, and that are not too small in the sense that their infinity norm diameter is at least 1 over n. And so there are only many such hyperplanes. In fact, I can give a bound on the numbers of hyperplanes of that type there are. And so here is the algorithm. It takes as data, as input my data, and the set of all subsets, the family that I'm going to consider. I need the level alpha as well, and the holder parameters for the class. So I'm going to compute the p-value for every hyperplane, hyperrectangle in my set, and set L hat to be the number of these different hyperrectangles. And then I'm going to order the p-values in increasing order. So of course, the one that's with the smallest p-value is giving me the strongest evidence that uniformly on that set, eta is above the level Tor. And then I'm going to apply Holmes multiple testing procedure to give me a sort of multiple testing correction here. So Holmes procedure is just the second simplest multiple testing procedure you can think of, where Bonferroni's method is the simplest, but Holmes procedure is just a little bit more powerful. You choose the largest curly L for which this inequality holds. So this is like the Bonferroni procedure. This is a way of controlling the family-wise error rate for arbitrary dependent p-values. And having then determined that the set of subsets of R to the D on which I think the regression function exceeds the level Tor, I then look at the union of those sets, and I look to try to maximize the empirical marginal measure of any set that both belongs to my family and belongs to the power set of the union of all these significant sets BL. Okay, that's the set I'm going to output. Okay, that might have been a bit of a mouthful, so let's go back to our example and look at a picture. So again, we've got this Gaussian class conditional distributions, and we've got our regression function eta as this solid black line, and the key level is going to be Tor is 0.8. And what I've got, these little blue lines here, are the p-values for the different hyperrectangles, which in this one-dimensional example are just intervals, and they're ordered as we go up the page from most significant to least significant. So what you can see here is that the most significant p-values occur around the kind of mode of the right-hand hump of the feature distribution, and that's because I'll tend to have larger values of this mu n hat of B in those regions. I'll tend to see more data. And there's a trade-off in terms of the length of the intervals, because the longer the length of the interval, the higher this level is, so that the higher the eta hat n of B needs to be in order for me to think that this is a significant p-value. But the more data I see, so this guy is inflated. So that there's a trade-off between small sets and large sets, but these are the p-values in their order. And then when I look at the union of all these significant p-values, well, it's very easy to choose the set that maximizes the empirical measure amongst all these, amongst the union of this, because it is just the whole union. That is an interval in itself. And so this is the set that I'm going to output. And notice in this case that it is indeed a subset of the Tor superlevel set of eta. That is, the interval that I'm outputting here lies entirely to the right of this green line. Okay, I mentioned before that I can extend these results from having just a beta less than or equal to 1 to general higher order smoothness. So this is a relatively standard definition of Holder smoothness. There are small variants that you'll see in the literature, but it's talking about how well I can approximate eta by its Taylor polynomial of a particular order. And then I want to make the sets nested, so I take an intersection over beta primes up to the level beta. There's another slightly more technical restriction I perhaps won't talk about in detail here, but this set curly R is a set of points where the marginal distribution is relatively well behaved. So this marginal distribution, if it was sort of locally constant, would be like the density at the center times the volume of the ball. Now I'm actually making this right-hand side larger than the density at the center because I'm taking a supremum of the density over the ball. And then I still want there to exist some epsilon that means I don't change things too much in that case. And I want that to be true for every R. So I want this set to be big, ideally. And I should have said before that one of the really the price we pay for working with general smoothness is that we do now need to assume that the marginal distribution is Lebesgue absolutely continuous, which I didn't have to before. Okay, so there are a couple of relatively common situations where I can argue that this set curly R is large when epsilon is sufficiently small. In fact, in this example, the third example I presented earlier, the set curly R is actually the whole of R to the D when epsilon is sufficiently small. And just extending our previous definition of approximable class, I want to have a further restriction now that insists that this A should be belong to the power set of this set curly R. That gives us another parameter, this epsilon in a class. I'm sorry for all the Greek letters. But the moral of the story is that the results can be extended to this setting and we get the same rates of convergence as we had before. So these are now holding for an arbitrary holder exponent beta. Okay, I want to say a little bit about how we construct the lower bounds in these arguments. Of course, if you want to construct lower bounds, you need to construct finite subsets of your parameter space with particular properties. There are actually two sort of fundamentally different constructions going on, giving three different lower bounds. And the first one that combines two things. One is giving me a lower bound that's giving me the right dependence on alpha, and the other is giving me a lower bound that gives me the right dependence, this logarithmic dependence in the numerator in the sample size. And the way we do it is illustrated in this picture here. So I've got a distribution where I pick ZL. So these ZLs, I don't really care where they are, they just need to be sufficiently well separated. And then the marginal distribution is going to be uniform on the union of the inner square and the kind of annulus square on the union of these things for the different over the different L's. But really more importantly is how here is how the regression function behaves. And the blue regions are where we're above the level tour, and the red is where we're below the level tour. So you'll notice that the curly ELF element of this construction, which is what I'm illustrating here, is different from the others because it's blue even in the center, whereas the others dip down below the level tour in the center. So you have to sort of choose things in such a way that you cannot confidently test which distribution you're from. So you don't know if you're in the one with L or L prime, so you don't know whether you're above the level tour, even in the middle bit or not. And if you get it wrong, then you're going to lose a lot of the measure, because you've got to output a convex set, and it can't contain this midpoint. So that's the kind of idea. You kind of lose a lot if you get the index wrong. And then the second type of argument we use for the lower bound is what gives us the parametric lower bound, the 1/√n rate. That's a little bit more standard as a construction, excuse me. So here again, blue is where we're above Tor and red's where we're below Tor. And the marginal distribution is uniform on each of the three squares here, but uniform with different levels. So that the light dots are lower density in the A0 region, where it's sort of medium level, and then we're higher at A1. Again, there are only two distributions in this construction, and I'm illustrating one of them. The other one would have the density of A-1 being larger than those of A1. And again, if you output the wrong set, if you get the index wrong, then you're going to lose enough in terms of the measure of these sets that you're going to get a 1/√n loss. Okay, so in the randomized controlled trial example at the beginning, really the situation was more like a treatment effect than just a simple regression problem, even though the regression problem is much sort of simpler to present at first. But I want to argue that I can extend the ideas to the heterogeneous treatment effect setting, where in addition to your covariate response pairs, you have a binary treatment indicator that I'll call T. I'm going to assume here that the propensity score, the probability that I could get treated given a particular vector of covariates, is known. And then I've got two different regression functions according to whether I'm treated or not. So what I'm interested then is the heterogeneous treatment effect, which I'll write as var phi of x. And then there are lots of definitions that you just need to kind of extend in the natural way from the regression function to the heterogeneous treatment effect setting. But the moral of the story is that you get the same minimax rates in this heterogeneous treatment effect setting. So you get this log n over alpha dependence in the numerator, all divided by the sample size and raised to this sort of interesting exponent here with a parametric floor. Okay, so let me wrap up then. I think from an applied perspective, probably the main takeaway message of this talk is that actually, despite the large literature saying that you shouldn't do subgroup selection, it is actually possible to do subgroup selection. It is possible to justify it, but it requires considerable care in the way that you formulate the problem. Actually, I don't want to argue that the way we have formulated the problem is the only way you could do it. I think the type 1 error control requirement that we make is actually a stringent one. That means that I think that's kind of appropriate in the randomized controlled trial setting, but it may be in other contexts that having more like an average control condition might be sufficient. Yeah, I think that's rather context dependent. So the way we formulate the problem is to seek a data-dependent selection set belonging to an interpretable class that contains as much of the population as possible, subject to a type 1 error control guarantee. Unfortunately, we found that it wasn't enough to have to work with a class of Lipschitz regression functions without any control of the Lipschitz constant. But if you do have work within known holder classes, then you can determine the minimax rates of the regret for any data-dependent selection set. Yeah, I think there are many different ways in which you could formulate this problem. I'm starting to think about some possible alternatives. I think this is potentially quite a wide open area at the moment, and I hope I might have piqued the interest of some of you in the audience. If you're interested in reading more, then this is the main reference on which the work is based. With that, I will stop and thank you very much for your attention.
Yeah, thank you very much for a great talk. I'll stop the recording and then we can see if people have questions.